Okay, so next speaker is Antonio Fernández from University of Bath, and he's going to talk on desingularization of vortices for the generalized surface-quasigeostrophic equation. Thank you.
Okay, so thank you, Denis, for the introduction. And also let me thank Benedetta, Francesca, and Alberto for the invitation. It's a great pleasure and an honor to be part of this meeting. It's been a while since we received the invitation mail, but I still remember the day. It was more or less a week after the defense of my PhD. I was still in Valencia and I ran to collect office. I was super, super happy. So thank you very much for the invitation. I just hope that very soon we will be able to resume this kind of meeting in person and see each other. And okay, so today I'm going to talk about a joint work with Manuel del Pino, who is also at the University of Bath, that concern a classical problem in fluid dynamics, which is called the desingularization of vortices. More precisely, I will focus today on the desingularization of vortices for the generalized surface-quasigeostrophic equation. However, before going into explaining what I understand for the desingularization of vortices problem and what I understand for the generalized Sqg equations, I would like to spend a couple of minutes, maybe a bit more, contextualizing the Sqg equation in the literature. To that end, let me consider in parallel two different equations. On one hand, I would like to consider a very, very classical equation, as it is the b-dimensional incompressible Euler equation that I wrote here directly in the vorticity string formulation. So these equations here. And on the other hand, I would like to consider the surface-quasigeostrophic equation that are this equation here. If one take a look to these two equations very, very quickly, one can see that they are very similar. We have the same kind of transport equation in both of them. We have, of course, the same kind of initial condition, but there is a difference, right? In the second line, in 2D Euler, we have minus Laplacian of C equal to omega. On the other hand, when we go to the Sqg, we have minus half Laplacian of C equal to theta. But you can say to me, okay, it is just an elliptic operator. We understand nowadays very well the fractional Laplacian, so they should be very close. Actually, they are not so close. And the mathematical question that I address nowadays for one equation and the other are very, very different. Let me just give a very brief example. If we consider an initial data here, omega 0, that belongs to L1, L infinity, it is by now classical that you have a solution that exists globally in time. It is a global in time solution, it is unique, everything goes very well. On the other hand, if we consider here for the Sqg an initial condition theta 0 that belongs to all the good spaces we want, say infinity with compact support, etc., it is not known if the solution of the Sqg equation is unique and global in time, or it may develop singularities in finite time. This is a massive open problem in PDEs. So the mathematical challenge that one equation and the other present nowadays are very, very different. Despite the fact, we can still consider an S-dependent family of equation, this family of equation here, that includes both of them. Here we have a dependence on S, and it is clear that if we consider S equal to 1 over 2, we are talking about the Sqg equation, and if we consider S equal to 1, we are indeed talking about the b-dimensional incompressible Euler equation. But you can say to me, okay, you have defined here an operator as a singular integral, and this definition works only if S is strictly smaller than 1. But we have a very nice property of the fractional Laplacian that says to us that if you consider the S Laplacian of a smooth function and you do S goes to 1, then you recover the Laplacian of that function in the pointwise sense. So we have somehow a certain continuity in this family of equation with respect to S. This family of equation is that I'm going to call the generalized surface-quasigeostrophic equation in the case where S is different than 1. And this is the family of equation for which I would like to address, or I would like to analyze a bit, the desingularization of vortices problem. Okay, this is the end of my talk, but I would like to spend 2 more minutes giving a bit more context about the Sqg equation and the generalized surface-quasigeostrophic equation gSQG. Okay, on one hand, I would like to talk a bit about the modelization of the Sqg equation. I'm not a total expert in modelization. I don't know almost anything about modelization. So what I did was to study a bit to prepare the talk. And what I learned is that the Sqg equations model the evolution of the temperature from a general quasi-geostrophic system for an atmosphere or an oceanic flow. Here, theta represents the potential temperature, U is the fluid velocity, and C can be identified with the pressure. So these are the physical quantities involved in this equation. But actually, the Sqg equation are derived from a more general quasi-geostrophic equation, which is settled in a half plane in 3D using a Dirichlet to Neumann map. All this I learned from the introduction of the thesis of Ludovico da Cagedillac. It is very nicely written. He explained very well the modelization of the Sqg, also of the gSQG, and he was a PhD student of Didier Smet and Philippe Javeillard. And also, he explained not only the modelization of the Sqg equation, he also explained how to obtain the gSQG. So the gSQG is not just a mathematical tool. Indeed, the kind of Dirichlet to Neumann map that reduces a problem on a half space in 3D to a problem on the boundary in the half space is the same kind of Dirichlet to Neumann map that is used in the so famous paper of Caffarelli and Silvestre about the extension for the fractional Laplacian. So if we consider a different Dirichlet to Neumann map with a different weight, we don't have here a half Laplacian, we have an S Laplacian. So this is why this is another reason to study the gSQG equation. And on the other hand, I would like to compare the Sqg equations with the 3-dimensional incompressible Euler equation, not the b-dimensional. Now we are talking about 3 dimensions. So let me consider again the Euler equation now in 3D that I wrote here directly in the vorticity string formulation. So this system here, let me just say that this, and this are vectorial equations. So we have a system of vectorial equation. And what is nowadays very well accepted is that the Sqg equation are a good model to understand 3D Euler. This was already pointed out in 1994 in a very nice paper of Konstantin Maddan Tabak. They compare numerically and analytically the Sqg equation with the 3-dimensional incompressible Euler equation, and they stress several analogies between the two equations. I just chose here 3 of them, but I would like to focus on the last one that concerns blow-up phenomena. I would like to read one phrase that they wrote in their paper. And they claim, one of the main themes of this paper is the use of Sqg as a simpler but analogous model problem for formation of singularities for 3D Euler. One of the main open problems that we have nowadays in PDEs is to understand the formation of singularities for 3D Euler. It's one of the biggest open problems. And what they are somehow claiming, and what is more or less accepted nowadays in the fluid mechanics community, is that the people that manage to understand the formation of singularity for the Sqg equation are in a very good path, or they may have ideas to understand the formation of singularities for 3D Euler. So I really think that this phrase here have generated a massive literature concerning the Sqg and the generalized Sqg equation. Okay, once this introduction is done, I would like finally to pass to explain what I understand for the desingularization of vortices problem. Let me just recall you that what I'm calling the generalized surface-quasigeostrophic equation are this equation here, and stress that during the rest of the talk, I will deal with vortex solution to the gSQG equation. Broadly speaking, a vortex solution to this equation is a solution for which the active scalar theta is highly concentrated around a number of points, a finite number of points. Let me emphasize that the analysis of vortex solution is actually a very, very old mathematical subject. Indeed, in the case of 2D Euler and 3D Euler, we can trace back the vortex solution until the 19th century, We have several papers of Helmholtz, Kirchhoff, and Ruth where they are already talking about vortex solution to the Euler equation in 2 dimensions and in 3 dimensions. Okay, so I would like to start to deal with vortex solution with a formal analysis. Let me introduce these two guys here. On one hand, I would like to consider formal theta, which is a sum of Dirac masses centered at different points. And on the other hand, I would like to consider formal C, which is the sum of several fundamental solutions of the fractional Laplacian in dimension 2 centered at different points. Here, kappa 1, kappa n are just the intensities of the vortices, and C1, Cn from 0t to R2 are just suitable functions. One can easily check that formally, let me just emphasize one more time this work. Formally, I'm not claiming any rigor on what I'm about to say, but from a formal point of view, one can check that formal C, theta formal C is a solution to the gSQG if and only if C is a solution to the following system of ODEs. So finally, some ODEs. Now I'm in the scope of the conference, ODEs and PDEs. Okay, so having at hand this formal analysis and this relation between this system of ODEs and the gSQG, we can finally formulate what I understand for the desingularization of vortices problem for the gSQG. And it is just one question. Can a singular vortex solution, as the formal solution that I described before, be regularized into a true, regular, smooth solution to the gSQG? So this is the question that I would like to address from now on. Okay, let me start with the case of 2D Euler. Despite the fact that the vortex solution were already considered many, many years ago, the desingularization of vortices problem was for the first time mathematically rigorously addressed in 1983 by Marchioro and Pulvirenti. They assumed that there exists a collisionless solution. I will come back to this word later. They assumed that there exists a collisionless solution to the system of ODEs that I wrote before in the case s equal to 1. And they managed to prove that in this case, there exists a solution, a true solution to the 2D Euler equation, depending on a small concentration parameter epsilon, such that in the distributional sense, when epsilon is going to 0, this solution converts to the formal solution that we described before. Note that this G1 here cannot be the same that I wrote before, because in this definition, that is the fundamental solution of the fractional Laplacian, we cannot take it s equal to 1, it doesn't make sense. Here, G1 is just the fundamental solution of the Laplacian in dimension 2. Okay, so somehow in 1993, Marchioro and Pulvirenti solved the desingularization of vortices problem for the case of 2D. However, very recently, Juan Davila, Manuel del Pino, Monica Musso, and Yun-Chen Wei revisited the result of Marchioro and Pulvirenti using a completely different approach, and were able to capture in a much more precise way than this asymptotic convergence the behavior of the solution when we are close to the vortices. Actually, they were able to obtain a point-wise estimate on the behavior of the solution omega epsilon psi epsilon to the Euler, even when we are going close to the vortices. Another advantage of the paper of Juan Davila and all is that they were able to deal with the more complicated for this problem. It is not always the case, but for this problem, it's more complicated. The case of a bonded domain. Okay, so in the case of 2D Euler, we have a quite satisfactory answer to the singularization of vortices problem, but taking into account the importance that the Sqg equation have received now in the literature and the fact that the equations were quite similar, a very natural question is try to understand if we are able to desingularize vortex solution to the gSQG equation. And a first thing that we wanted to analyze is if there was already something done in the literature. And the answer is yes. There are several papers that already consider the desingularization of vortices for the gSQG equation. most of this paper goes on the line of Marchioro and Pulvirenti. We have a paper of 2013 of Cavaraggio, Garro, and then Marchioro, and then we have two very recent papers, one of Geldauser-Romito and one of Matthew Rosenberg, all of them using the same kind of technique that the paper of Marchioro and Pulvirenti and addressing the desingularization of vortices problem. However, all these results are partial results. On one hand, the result of Cavaraggio, Garra, and Marchioro and the result of Rosenberg are conditional results. If you go through the proof, at some point you realize that what they are assuming is that you have a theory of existence and uniqueness of solutions that are global in time for the gSQG equation. And this is a massive open problem. It is not known. So you need somehow that the interval of the existence on time of the solution of the gSQG and of the point vortex model, the intersection of these two intervals is not empty. So they are both of them conditional results. On the other hand, the paper of Geldauser-Romito is not conditional, but they need that S belong to a square root of 3/2, 1. So somehow they need that S is sufficiently close to 1, and then they are able to, using the kind of approach introduced by Marchioro and Pulvirenti, have the distributional convergence, have a partial answer to the singularization of vortices problem. On the other hand, there exists another result that goes in our line of research, but it is still a partial result. Using a Lyapunov-Smith reduction, Wei Yao, Juan Davila, Manuel del Pino, Monica Musso, and Yunchen Wei have very recently constructed traveling vortex solutions to the gSQG that concentrate near certain critical point or certain solution to the system of ODE PPM. Let me emphasize a couple of things with respect to the solution of Wei Yao and all. They are able to do or to solve the singularization of vortices problem for certain solution of the system of ODEs. They are not able to deal with all the solution to the system of ODEs, but to some of them. And on the other hand, I would like also to emphasize that the solution that they are able to construct do not change form as tiny balls. Indeed, what they do is to reduce everything to the analysis of an elliptic equation, and then they construct solution to this elliptic equation that concentrate at certain point. Okay, and these are the certain points that are solution to the system of ODEs. Okay, so our aim can be now formulated as follows. But first, let me just remind you that this is what I'm calling the gSQG, and the system of ODEs that I'm referring all the time is this one. Okay, and finally, our aim. Our aim is to solve the desingularization of vortices problem in its full generality for the gSQG. Let us assume that there exists a solution, as in the paper of Marchioro and Pulvirenti, to the system of ODEs that has no collision on 0t. And this is what I understand for having no collision on 0t mathematically. And what we want to do is to construct. We are going to construct the solution. We are not using any theory of existence. We are going to construct the solution. We are going to construct a regular solution to the gSQG depending on a small concentration parameter epsilon, check that when epsilon going to 0, our solution will converge in a suitable sense to the formal solution, formal singular solution that I described at the very beginning. So this is precisely what means to solve the desingularization of vortices problem. And in a suitable sense, I will precise it later, but we will have at least the distributional convergence a la Marchioro Pulvirenti. How do we do this? Let me start with explicit epsilon regularization of the singular solution that I described at the very beginning. And to that end, I will use the fractional Yamabe problem. So what we are going to do is to use the so-called bubbles to linearize the gSQG flow. So we are going to linearize the gSQG flow around this bubble. So let me introduce this function gamma 0 and recall you that, as Begoña Barrios explained yesterday, it is well known that under suitable decay assumption, all the solutions to the fractional Yamabe problem are of this form here. And we have very nice properties of this function because we know that the linearized operator around this bubble is very well understood. We understand the kernel. So this is why we choose to linearize the gSQG flow around this bubble. And this function gamma 0 and u0 are going to be the basic cells that we use to construct our solution to the gSQG. More precisely, let me introduce these two functions here, where C0 is just the sum of different function gamma 0 with different rescaling centered at different points, and theta 0 is just the same, but for u0. These are indeed explicit epsilon regularization of the formal solution that I described at the very beginning. If we remove here the epsilons, then we have our formal solution from the very beginning. So having at hand this explicit epsilon regularization, we achieve our aim constructing an epsilon dependent solution, which is of this form here. So we have the explicit part, which is related to this function, plus a remainder we depend on epsilon, and we have to control. Okay, here it is exactly unequal. Here it is an approx because we need a small technicality to deal with theta 0. But the idea is that at main order, these are the two basic cells to construct our solution. And let me just be a bit more precise and state our main result. So assume that S belongs to 1/2, with both of them included, and let C0 be a solution to the system of ODE that I wrote at the very beginning, with no collision in 0T. As I said before, there exists a smooth solution to the gSQG, a true solution to the gSQG of this form that satisfies the convergence a la Marchioro Pulvirenti, but not only that, we have a very precise control in the two remainder terms. We have a pointwise control in the two remainder terms. So we don't have only a distributional convergence, we are able to control in the pointwise sense the behavior of the solution we construct, even when we are very, very close to the vortices. Okay, so this is the main result we have obtained, and this is how I imagine the solution. I'm not saying this is true. There is even a boundary, and I'm working in R2, so it's not possible that it's like that. But this is how I imagine. So I imagine that we have our function C1 up to C5 that are moving on the plane, that are interacting with each other, and then we are constructing a solution that when epsilon is going to 0 is getting sharper and sharper and sharper. So this is how I imagine our solution to be. Okay, and during the rest of my time, I would like to say some words about the proof of this result. Let me start with the three main steps of the proof. This is the sketch of the proof. The first thing that we have to do is to improve our approximation. What we have done up to now is to imagine that the function that I introduced, C0 theta 0, are a good approximation to be solution of the gSQG equation. However, when we go close to the vortices, this is not at all a very good approximation. And this is a quite bad approximation. It is good when we are from the vortices, it is good when we are in an intermediate region, but when we are close to the vortices, it is very, very bad. So what we have to do is to find a better approximation. And to do that, we are going to look for an approximation which is of the form C0 plus something and theta 0 plus something. We find this better approximation solving approximately an inner-outer system. I will explain a bit later what is the form of the solution. I will come back to this. Once we have our better approximation, what we are going to do is to look for a true solution of the gSQG, which is of the form theta star, C star plus something, theta star plus something. This something has to be, again, chosen in an appropriate way. And we are going to do this using a second in and outer system. We set up the problem as a coupled system of n+1 problem, one problem near each one of the vortices and an outer problem. And then if we manage to solve this in an outer system, we are done. To solve this system of equation, we are going to use topological degree approach. So the key to solve this to solve this using a topological degree approach, as we all know, is to obtain suitable a priori model. Okay, so these are the three main steps of the proof, and I would like to focus in my remaining more or less 10 minutes in how do we do to improve the approximation, that I really think is the most involved part of the paper. It's almost 60 pages to improve the approximation. It's very, very large. And also to give a couple of lemmas that have been key to obtain a priori bound. They will seem a bit unrelated to the problem I'm discussing, the two lemmas that I will give, but they are actually the key to obtain the a priori bound. So let me start with the improvement of the approximation. We are going to restrict our choice of the point C, that, as I said before, is not the solution of the point vortex model, but a perturbation. We are going to restrict ourselves to choose C of the form C0, the solution of the point vortex system, the system of ODE, plus three functions that we are going to choose during the process of the first approximation, plus a remainder that we are going to choose to solve the final inner-outer system. Then, having at hand our choice of the form of C, we are going to look for an approximate solution, which is of this form here, that, as I promised before, is going to be C0 plus something and θ0 plus something. This something is carefully chosen in a way that our choice will rewrite the gSQG equation as a coupled system of n+1 equations, an equation that are close to each one of the vortices and one equation more, which is the outer problem. And then we look for a solution of this form, and we have to find all this function and part of C. So to do this, we do several steps. We are not going to solve the inner-outer system, but we are going to solve it approximately. We're going to keep improving our solution until the error is small enough for us. The first improvement that we are going to do is an elliptic approach. We are going to analyze linear elliptic equation, harmless apparently, of this form. An operator L equal to a function f, but our operator L is very ugly. We have the linearized operator around the bubble for the fractional Yamaga problem and 0, and then our operator L is the angular derivative of this operator multiplied by a way. This is very ugly because, for instance, all the radial functions are on the kernel of the operator. So when you want a solvability theory of this type, it's not very nice. So it's a bit tricky to obtain the solvability theory, but you work a bit with the fractional Laplacian by hand. You have to be a bit careful with the Fourier modes. You interact a bit with the Fourier series and the fractional Laplacian, that they are not very friendly, but you manage to obtain a solvability theory for equation of this form, and then you use this solvability theory as a black box. We have to deal with 7 different right-hand sides, but you improve as much as possible using this elliptic approach until it blocks. At some point, you cannot continue improving elliptically, but you realize that you can do other things. Your inner equation has also a transport equation approach. So you can use transport equation theory to continue your improvement of the solution. And we are led to deal with transport equation of this form. Again, we have a suitable solvability theory with the properties of the solution. We deal just here with 2 right-hand sides, And combining these two approaches, we are able to find several functions that give us an error that for the inner problem is small enough. And then we are very happy, and because the inner problem are supposed to be more difficult, but still we have to deal with the outer problem. We go to the outer problem and we realize that it's not as simple as in the local case, because the fractional Laplacian is not very friend of this cutoff that we have. So you have to work a bit, but the idea is the same. You combine your elliptic approach with your transport equation approach, and you improve the outer approximation. So you have improved the inner error, you have improved the outer error, and you are very happy. The problem is that your improvement of the outer approximation introduces an error in your inner problem. So you have basically destroyed a bit your very good inner approximation. So you have still to work a bit more and to improve one more time your inner approximation. But again, we have our black box containing the solvability theory for your linear operator, and you just have to do the same kind of approach, and we finally arrive to a good enough approximation that, as I promised, is of this form here. And finally, I would like to give two lemmas that have been key for the derivation of a priori bound. Let me introduce some notation. I would like to introduce this function theta L from L with L from 0 to 3 that are basically related to the kernel of the linearized problem for the fractional Yamaha equation. And assuming that we have a function belonging to a L2 weighted space that is orthogonal to this element, we are able to obtain a lower bound in the solution of a weighted Poisson problem in dimension 2 that is really the key to the obtain of a priori bound. This estimate that is apparently related to our problem is really the key to obtain suitable a priori bound to our problem and to be able to conclude our topological degree argument. And the key is that we have here an explicit dependent on R. Okay, I gave here a couple of references to the proof of this lemma, but if someone knows this reference, he or she can say to me, okay, there is nothing to see. The paper of William Beckner deals with Sobolev inequalities in the sphere, and the paper of Rupert Frank and Edwin Lee with the deal with sharp constant for the Hardy-Littlewood Sobolev inequality. So why I'm giving this to reference? Let me introduce some more notation. What we want to do is to put everything on the sphere. So I recall you that this is the stereographic projection, the inverse, and I introduced two different changes of variable over line F given this way, G tilde given this way, and an operator on the sphere, which is basically a risk potential on the sphere. Having at hand all this notation and all the very nice work done by Beckner and Frank and Leaf, we are done. Why? Because we can rewrite our scalar product of F times G and L2 on the sphere as this guy here. And then, using all the very nice theory that they have done, we can prove, that this is bigger than a constant, depending on S, over R, and the integral on S2 of P tilde square. You translate back this to R2, and this is exactly what you want. So we use all the very nice work that they have done to be able to conclude our a priori bound. To do that, we decompose the space L2 of S2 on this way, using the harmonic polynomials in R3, and we use all these very nice properties that they have managed to prove. They know that this is a self-adjoint operator, which is diagonal with respect to this composition. We know the eigenvalues, very nice. So we are basically done. So we have been very lucky because all what we have to do is to prove this inequality here, and Beckner, Frank, and Leaf have done the work for us. So we have been very, very lucky. Just one thing is that the first thing we did was to normalize all the constants. And this was a massive error because thanks to all the constants that we have here and the explicit value of the eigenvalues, we can have our result. So if you normalize the constant, you can do anything. And the final lemma that I would like to give is even simpler, because I would like just to emphasize a very tiny thing that we have spent a lot of time until we discovered this, using another things much more difficult, doing much more difficult computation. But this tiny lemma here have simplified our lives a lot. So let's see V a miserable function belonging to L2 weighted space, and let us consider the fractional Poisson equation in R2. We have realized that despite the fact that the fractional Laplacian is not conformal in dimension 2, you can still translate the Poisson equation to the sphere in a very nice way. And the key is to use two different changes of variable and not just one. Here we have overline f, and here we have tilde f. They are different changes of variable, and this is why we can obtain a nice equation. If you try to use just one chain of variable, you have an operator on the sphere that is degenerated on the point where you are doing the stereographic projection, and you cannot do absolutely anything. But the fact that you can use two different changes of variable gives you a very nice operator for which you have all the very beautiful estimate you need. You come back to the plane and you are done. So these two lemmas are really the key, even if they are apparently unrelated to our result. Okay, so that's what I wanted to say. Thank you very much for your attention.